Okay. Here's a little review of what we did yesterday. Okay, we're talking about different types of radiation, radioactive decay, what can happen. All right, and I really probably should have got back even before this and showed you that band of stability again. Okay, guys who are above the band of stability, they've got too many neutrons and not enough protons. Let me let's get that quickly. Actually, I want to get this one here. All right, so there's your band of stability. If you're up here, you got 80-some neutrons and only 20 protons, you're not happy. Okay, you got too many neutrons, not enough protons. So, what do you do? Well, let's take a look at what you do. If you're above the band, you can undergo two types of emission, beta emission or neutron emission, both of which would serve the purpose of reducing the number of neutrons or at the same time increasing the number of protons. Okay? So this is all from yesterday, and this is what we did. We did examples of each of these, all right, and you should be getting used to doing this. I gave some homework on it as well. Now, what about guys who are below the band? Well, guys who are below the band, they've got too many protons and not enough neutrons. So they're going to want to do the exact opposite. You should be able to, by the time I'm done, and tomorrow's going to be like kind of a catch-all. I'm going to do one new topic in a double period, but I'm going to use the time to do some other problems on the board, some other problems for the homework, and also going to show you that little video clip.
Juniors with last names beginning with the letter M, please report to the conference room with your enrollment sheet. Also, junior powder puff practice that was scheduled for tonight has been canceled. Senior powder puff practice for tonight has also been canceled and is rescheduled for tomorrow at 4:30 at the Salem track. Thank you.
Okay. All right. So if you're below the band, you basically want to do the opposite. You are going to undergo positron emission or electron capture to increase the neutron-proton ratio. You want to make more neutrons, all right? You want to get rid of some of your protons, one way or the other, and you'll see how that can happen. And I hope you'll see how, because although you can actually get a good grade on this without really understanding what's going on, just by balancing the equations, just by looking at, make sure the atomic numbers balance on this side and the mass numbers balance on that side. It's nice if you understand why they're doing what they're doing. So I'll try to explain that to you too. All right. All right, let's talk about the first one, positron emission. Let's see what's going on here. All right, positron emission. If you were to look back at the previous one, beta emission, a neutron was converted into a proton. Well, in positron emission, guess what happens? Can you make a guess at it? Is it not a...
You have emission spelled two different ways.
I'm sorry.
You're throwing me way off.
Well, which one's right? I don't know.
The first one. First.
Yeah, I had too many M's there, huh?
And you have one less S.
Emission. I got two. Yeah, that's where the other one went. Okay. Wow. All right, I got to fix my spelling. Okay, if we can get over that. All right, maybe we can just look past that for a second. Again, let's go back one more time. In a beta emission, where I've got too many neutrons and not enough protons, I convert a neutron into a proton. What do you think is going to happen in positron emission?
You take a neutron to a proton.
I just said it's with the other.
A proton into a neutron.
Yeah.
I know it's the opposite way. I just didn't know what it was.
Yeah, and that makes sense. I would want to do that because I want to get my protons. I have too many protons. I want to get rid of my protons, and I want to increase my number of neutrons. Okay? And I'll do an example of one of those. Say I take potassium 37. Now, really the only hard part of these is remember what each of the particles mean. That's really the most important, most difficult part of this, honestly, because once you know what the particles mean, you almost can't screw it up as long as you can add or subtract one or two numbers. Okay? You know you're going to get two things here, right? One of them's a positron. Problem is, what's a positron? Take a look. Look back at my types of radiation. What do I use to represent a positron? If you look him up, you'll see he's this, isn't he? Right? That's a positron. If that is a positron, and can I balance this out? Now it's just a matter of looking at the math here. I've got 19 on that side. I've got a 1 on this side. What must be the atomic number of this mystery element? 18, because 18 and 1 is 19. What must be the mass number of this mystery element? 37. What's the symbol of this mystery element? AR, which stands for R. This is a pirate element. R. No, it's argon.
It's art.
Because if you are not here, you are gone. Okay. And it is art. Art.
Art B.
Art B. Arthur B. Okay. B. Arthur. B. Arthur is actually a famous. Was she from the Golden Girls, right? B. Arthur.
My grandfather's name's Arthur Boone.
Arthur Boone. Also, this is freaky.
Is he 37 years old?
Yeah. And she's almost 18, and he's 37, and they have a child who's 1. I don't think so.
My
right.
dad's not even 37, he's like 42.
All right. Anyway, so that's positron emission. Let's do another one quickly down below. And the second one I want to show you something. Remember, in the homework that you're going to get tonight, and in the board, the ones I'm going to do on the board tomorrow, I won't always just give you, here, what happens in positron emission and give you the left side. Sometimes I'll leave a blank. Okay? So if I gave you this much information, if I gave you the fact that it was, wait a minute, that it was nitrogen produced over here and positron. And by the way, the positron can be written as, I wrote that last one as a B, a script B looked like, all right? I could also have written it as E with the 1. Okay, it's like a positively charged electron. If I gave you this much information, could you tell me, and I left this blank, could you tell me what that came from?
Is that a scrawny looking 7?
It's a scrawny looking 7, yes. What must this guy have been over here? I mean, I could do it in any order and leave any one of these blank. What do you think? What element was this guy over here?
Oxygen.
Exactly. It's oxygen because it has to be 7 and 1 is 8. 15. It's got to be oxygen. Okay? All right, easy enough. Now, positron emission makes sense because if you look at it, and this is the way you have to look at it, if you were trying to explain it to me, if I asked you to explain it to me. This guy's got 19 protons. He's only got 18. I lost a proton, but I didn't change my mass number. So therefore, it must have been changed into a neutron. And that's exactly what happened. Protons changed into a neutron. There's another way I can do that, though. I can capture an electron. Now, this is, again, going to seem weird to you. What do you mean capture an electron? Like I'm going to make an ion out of it? Like, fluorine gets an extra electron, becomes -1. Oxygen gets -2 when it gets 2 electrons? No. Not that kind of electron capture. I'm not talking about the transfer of electrons between orbitals in atoms, but rather an electron being captured by a nucleus, in which case the proton is again converted into a neutron. But this is different. It is not the emission of a positron, it's the capture of an electron. Both will end up with the same result, which is the conversion of a proton into a neutron. I'll just do one example of this guy. Now the weird part about this is, most of these have been like that, an element and then a yield sign, an element and then a yield sign. This is going to be an element adding a beta particle to it, an electron. I'm adding an electron to this guy's nucleus. Well, again, even if you don't totally understand what the heck's going on down there, you can balance this equation. 47 and a negative 1, what's got to be the number over here? 46. I always get people who want to say 48. And then 106 on the top. What element is number 46? Palladium. Right? Got it? Does that make sense, everybody? All right. And again, look what happened. This guy had 47 protons. This guy only has 46. Again, a proton was converted to a neutron, and mass number didn't change.
It's that backwards.
It is, exactly. It's like that backwards. There's a positron being emitted or an electron being captured.
All right.
Beta particle being captured. Okay. So those are ways you could get back to the band of stability if you are outside of it, below the band. Now, there's one other thing I want to talk, actually there's two other, but one other biggie, where I've got guys who are bigger than 82. Now, like a house of cards, if I keep adding stuff in here, it becomes more and more unstable. More and more protons, more and more neutrons in here. The larger the atom is, the more unstable it's going to be. And everybody over 82 is inherently unstable. All the nuclides above it. By the way, who is 82? The last stable element there. Can you see it? You guys are from here? 82? It is lead. And that's lead, not lead. Oops. Okay. So all the nuclides above 82 are inherently unstable and therefore radioactive. So they're going to try to get back to the band of stability. They have too many protons and neutrons. And one of the ways they can do that, one of the major ways that they do that, although not the only way by any means, is by giving off a large particle. And one of the larger particles they can give off radiation we've read about, we saw the other day, is what? Alpha particles, yeah. Larger atoms often decay by alpha emission. And I'm going to give you one here that we're going to deal with a great deal. Because you see, for a guy as big as uranium, which is what I want to give you here, uranium-238, a guy as big as uranium, who has 92 protons, and however many you subtract that from 238 neutrons, a guy that big can't get stable in one step. As a matter of fact, he can't get stable in a very short period of time. It takes hundreds of thousands, even millions of years sometimes, before something like this can decay, can give off enough particles to get down to be stable again. Okay? So uranium-238 in one step could give off an alpha particle. Finish that on your own. I mean, I'm going to put it up there in a second, but everybody should be able to do that. You say, well, I don't know how to do it. Why? Because you got to look up what alpha particle is. Look it up from just the last day. Write it down over here, and that's what it is, and then balance it out. If you looked up an alpha particle, you see that he is just a what? Well, you could use a fish, or you could use what? A helium nucleus. Either one would be correct. All right? But either way, whether you draw the alpha particle as this or as this, it's still 4/2, right? Okay? So, since he's 4/2, this must be 90, and that must be 234, which makes him thorium. Did you all do that? I hope. That's how you'll know what element this is. Because you have to add up on both sides to be the same. 90 and 2 is 92, 234 and 4 is 238. You know he's thorium by looking at your periodic table. Okay? All right, easy enough. But again, tomorrow we're going to learn how to do a disintegration series. Okay, a decay series for uranium in particular, yeah.
I won't be very long.
Okay, watch the video. It won't be very long. Despite the fact that it's a double period, I probably won't have more than one actual video. It won't take more than what I'm doing today, probably less. All right, probably about 15 minutes. Because I have other things we're going to do to just practice tomorrow. But anyway, if you look at that tomorrow, you're going to see that he can't get there. He can't get to be lead or below in one step. Because even giving this off, what's he going to have? He's still going to have 90 protons. That's still too big, still radioactive, this guy is. He'll have to go through a series of decays. Okay. The last type of radiation we wanted to talk about was gamma radiation. That's the stuff that turns the Hulk green. Bruce Banner. Not really. Just saying. Gamma radiation is, we have actually talked about it before. I know you probably don't remember it, but look at that poster up there. Remember this? Gamma radiation? Where did we talk about electromagnetic radiation before? When we were talking about the chapter on electrons. Remember when we did flame tests, quantum theory, all that stuff, right? Remember this equation? Delta E, don't write it down. You're not going to use it now. Equals hc over lambda. Remember doing that? It was a long time ago. It was like chapter 4. We're in like the 16th chapter we've done this year. So next to last chapter. Okay, the wavelength and the energy, we calculated it. This is Planck's constant, speed of light. Okay, the wavelength and energy were related. How are they related? They're inversely proportional. Look at that chart where gamma rays are. They're way up at the high end of the spectrum, very high frequency, very short wavelengths, as opposed to longer wavelengths, which have very low energy. So the smaller the wavelength, the more energy they have. Gamma rays have a lot of energy. Okay, and that's why they're dangerous. That's why we're going to talk about, by the way, if you're wondering why I haven't already been talking about health effects of radiation and stuff like that, I have a whole section on that. We're going to do like a couple of days probably on that, at least a couple of periods, maybe a couple of days, on health effects of radiation. Gamma rays are some of the worst. However, they happen to be some of the easiest to do these formulas for. Gamma rays are just electromagnetic radiation given off when radioactive atoms drop to a lower energy state. Now, it's not exactly the same, but think about, do you remember when we did those flame tests for delta equals hc over lambda? Remember how I talked about the quantum theory when electrons got excited, when they fell back down, they gave off energy that we saw as light, and depending on what color of light was given off, told me what element it was. I was able to identify the element. Well, the same thing's true for gamma radiation. When these unstable nuclei now, not electron clouds, but nuclei drop down to a lower energy level, law of conservation of matter energy holds. He's got to have to give off energy in order to drop down there. All right, and that's the electromagnetic radiation given off. And it sometimes happens along with, it accompanies some other types of radiation. Now, the reason these guys are so easy to do compared to the other ones we've been doing, and the other ones weren't hard either, is the second half of this statement right here. The number of protons and neutrons has not changed. I don't change anything about the actual atom, the nucleus, except for its energy state. I don't change the number of protons. I don't change the mass number or the number of neutrons. So what does the equation look like? Well, let me just show you one. If I take iodine 125 and I have it give off some gamma radiation, it will still be iodine 125. That little asterisk or star or whatever they put above them, sometimes they use to illustrate or to indicate, I should say, an energized atom, an excited one. All right. And there's your gamma radiation. Remember this? That's a symbol for gamma radiation. Now, remember this. On the test, I will ask you, and also in the homework tonight, I'm going to ask you, I'll put a block around something, and I'll leave that blank, or I'll leave this one blank, or whatever. If you see that were your blank, and you saw this guy was exactly the same as that guy, you would know it's gamma radiation given off, because it's the only one that doesn't have any charge or any numbers associated with it. No protons, no neutrons, nothing. Okay, and vice versa. If I had that in there and I didn't have this here, you know it would be exactly the same on the other side. Okay, same number of same mass number, same number of protons. Okay, all right. So some of the homework tonight, and I don't know if you do not feel like you have to finish this tomorrow. I mean for tomorrow. I will not check it for you guys. The other class had an extra time to do it. So you're going to have that extra time tomorrow, so I'll probably check yours on Monday. So don't feel like you have to finish these for homework, but this is your homework for tomorrow, okay? And you can copy that down, and you can start it now, but you will have time in class to finish it tomorrow.